Okay, so next topic is activity in solutions.
सर
Yes.
सर ते जनरलाइज चार्ट युजिंग आपण काढतो ना त्याला repeat करायचं.
No Marathi, please. I'm not very good at Marathi.
सर ते डिटर्मिनेशन ऑफ फ्यूगोसिटी ऑफ प्योर गैसेस था ना, उसमें वो हमने वो जनरलाइज चार्ट यूज किया था
Generalized?
सर. फ्यूगोसिटी ऑफ कोएफिशिएंट वर्सेस रेड्यूस प्रेशर का वो चार्ट था ना,
हाँ,
वो सर समझा नहीं था.
अरे उसको तो एक हफ्ता हो गया अरे टॉपिक को.
हाँ सर, रिवाइज किया था अभी.
ठीक है, 1 मिनट. ये चार्ट क्या दिख रहा है ये रितेश?
हाँ हाँ सर, वही.
इसमें क्या नहीं समझ में आया? क्या डाउट क्या है?
सर वो क्रिटिकल टेम्परेचर लेके वो कुछ करते हैं ना, वो ऐसा.
नहीं, रिड्यूस प्रेशर क्या होता है?
तो एक्चुअल अपन क्रिटिकल लेते हैं हम.
राइट, व्हाट इज रिड्यूस प्रेशर?
सर एक्चुअल प्रेशर अपन क्रिटिकल प्रेशर.
Actual upon critical. So if you are going to find out fugacity at any pressure, you know the pressure, right? So we know the reduced pressure also. कोई भी component लेंगे, suppose you take nitrogen, oxygen, hydrogen, तो उसका critical pressure is available. The data is available, right? And if you want to find out at certain pressure, तो PR पता है हमारे को, reduced pressure, और at a certain temperature, तो TR भी पता है. TR is T upon TC, बराबर? So PR and TR पता है, तो we can find out what is the fugacity coefficient from एक्स एक्सिस से ऊपर आने का, और जो टी आर पर इंटरसेक्ट होगा दैट इज़ योर पॉइंट, और वहाँ से इधर वाई एक्सिस पे जाने का. सो दैट इज़ योर फिगेसिटी कोफिशिएंट एट दैट पी आर एंड दैट टी आर. सपोज आई वांट एट रिड्यूस प्रेशर ऑफ 40, तो 40 का लाइन में ऊपर आने का. एंड सपोज आई वांट एट रिड्यूस टेम्परेचर ऑफ से 6, राइट? तो यहाँ से इधर लेंगे, इट विल बी समथिंग लाइक 1.8. That is the fugacity coefficient at reduced pressure of 40 and reduced temperature of 5 or 6, sorry. fugacity coefficient पता चलेगा तो fugacity निकाल सकते हैं हम.
यस.
और कोई डाउट था इसमें? तो डिफरेंट स्केल दिया है यहाँ पर, ये रेंज अलग है यार. यहाँ पर 0 से 20 पी आर है, यहाँ से 0 से 100 पी आर है. ये वाइडर रेंज का है, ये लोअर रेंज का है, राइट? वैसे टी आर इज फ्रॉम हियर इट इज सॉरी 5 टी आर टू 35 टी आर. यहाँ पर है 1 टी आर टू 3 टी आर. सो जिस रेंज में रहेगा उस रेंज का ग्राफ यूज़ करने का. यू कैन यूज दिस रेंज, दिस ग्राफ in this range of PR and TR, and this graph for this range of PR and TR. Once you get that fugacity coefficient, you can find out the fugacity, right? It is nothing but ln f by p. f by p मिलेगा, प्रेशर पता है, तो you can find out what is fugacity. ठीक है?
यस सर.
ओके. और कोई डाउट है किसी को? ओके. नहीं है तो let us proceed to the next topic, which is activity in solutions. So last week we defined Lewis fugacity rule. What is Lewis fugacity rule? Who can tell me?
Fi equal to yi into Fi.
Fi bar, not Fi.
Fi bar equal to yi into Fi.
Yes. So if you know the pure component fugacity and you know the mole fraction in the solution, then we can find out the fugacity in the solution. Right? That's what Lewis fugacity rule is. That is applicable for what kind of solutions? कौन से solutions के लिए applicable है Lewis fugacity rule? Ideal solutions, right? Ideal solutions का मतलब क्या है?
सर जिनके पार्शियल मोलर प्रॉपर्टीज मोलर प्रॉपर्टीज.
Partial molar property equal to molar property, but main thing is that is a derived thing. Conclusion. Main thing is there is no volume change on mixing. Definition of ideal solution is when I mix two pure components, gas or liquid, doesn't matter. There is no volume change on mixing. So if I take 1 liter of ethanol and 1 liter of water, if they are ideal solution, if they form ideal solutions, it should give me 2 liters of methanol. बट ऐसा होता नहीं है, बराबर ना? हमने देखा था इथेनॉल वाटर डज नॉट गिव द सेम वॉल्यूम, ऐड किया तो उतना नहीं मिलता है, कम मिलता है. सो दिस इज नॉन आइडियल सॉल्यूशन. सो वी स्टार्टेड विद आइडियल सॉल्यूशन assuming that there is no volume change on mixing when you mix two components, pure components, to form a solution. That is the definition of ideal solution. Right? तो उसके लिए लुईस फिगासिटी रूल हमने डेराइव किया था. ठीक है. नाउ लेट अस लुक एट सॉल्यूशंस में एक्टिविटी क्या होता है. Activity is ratio of fugacity of a component in solution divided by fugacity of the components in standard state. So we are defined standard state, right? Standard state is generally pure component at same temperature and pressure. So we define AI is equal to Fi bar upon Fi 0. ठीक है, ये पहले भी डिफाइन किया था हमने. We are going to use this now. And we know that mu I is partial molar Gibbs free energy is equal to RT ln Fi bar plus C, and mu I naught is equal to RT ln Fi 0 plus C. So delta mu I is nothing but mu I minus mu I naught equal to RT ln Fi bar by Fi naught, which is nothing but RT ln AI. ठीक है. And delta mu I is increase in chemical potential of component I when it is brought into solution from its standard state, from pure component. And if standard state is pure component at temperature and pressure, so that's what we do, right? We define standard state as pure component. In that case, AI is equal to Fi bar upon Fi naught, which is nothing but Fi naught is equal to pure component fugacity. So this is equal to Fi bar upon Fi. ठीक है, ये जस्ट रिवीजन है. एनी डाउट्स ऑन दिस? नया नहीं है, पहले भी किया हमने. Okay.
No, sir.
Okay, so for ideal solutions, we have seen Lewis fugacity rule Fi bar is equal to Xi into Fi, right? So if I put Fi bar is equal to Xi Fi in this equation AI, इसको यहाँ substitute किया मैंने, तो what I'll get is AI equal to Xi. ठीक है. Any doubts on this? Ideal solutions के लिए we can say activity is equal to nothing but mole fraction. ठीक है. Any questions on this one? ठीक है. So let's go to activity coefficients. What do they do? Activity coefficient measures the extent to which real solutions departs from ideal solution. Because we are always talking about deviation, right? We always talk about deviation. कितना ideal है, तो now we have to see if you want to find out the activity of real solution, we need to find out how much it deviates from ideal solution. It's easier to calculate that. So gamma is defined as activity coefficient, and what we do is we take this Lewis fugacity rule, which is applicable for ideal solutions, and reduce gamma here to account for non-ideality. So that equation becomes nothing but Fi bar is equal to gamma I xi Fi0 or Fi. Same thing, Fi0 is equal to Fi, right? So this is now applicable for real solutions. So now we can find out the fugacity of component I in solution when the solution behaves as a non-ideal solution. समझ में आ रहा है? So this gamma will account for कितना deviation है from ideality. अगर 1 है gamma, if gamma equal to 1, then it is loose fugacity rule. That means ideal solution. If gamma is more than 1, then it is called positive deviations from ideality. And if gamma is less than 1, it is called negative deviations from ideality. We'll see that later. But let's not worry about the positive and negative. Basically, this accounts for कितना difference है between ideal and real solution. Okay, so gamma is activity coefficient of I in solution, and Fi naught is fugacity in standard state, and we define standard state as pure component. That's why Fi naught equal to Fi हो जाता है. So for ideal solution, gamma I equal to 1, and it reduces to Fi naught is equal to xi, Fi bar is equal to xi into Fi naught, which is nothing but xi into Fi, considering standard state as pure component. So this equation will reduce to loose fugacity rule, loose random rule for ideal solutions. Any questions, doubts on activity coefficient? Why it is? What are we doing with it? Understand what we are doing. जैसे मैंने last time बोला था, we always start with ideal and then see how much is the deviation from ideality, what is the deviation from ideality, and build that into it. अभी हमने ऐसे किया, we defined ideal solutions and found out fugacity of component in solution. Now we are saying ठीक है, अगर ideal है तो ये है, non ideal हुआ तो क्या होगा, कैसे change होगा. So we put a factor gamma I, which we will determine later on. You'll see a lot of methods of finding of gamma I activity coefficient, which will tell us exactly what will be the fugacity in solution for the component when it is not ideal. When it is ideal, gamma I equal to 1. So that reduces to loose random rule. ठीक है?
Yes, sir.
Okay, so this is pure liquid at standard pressure at standard state. Fi not equal to Fi हो जाता है. Right? So there are two types of ideal behavior. We have seen this before. Now this ideal behavior जो हम बोल रहे हैं, there are two types of ideal behavior. We will see that now. One, the first one follows Lewis random rule or Raoult's law. Raoult's law भी देखा था हमने last week. That is pure liquid at system pressure as standard state. Okay. So in this case, Fi bar is equal to gamma I xi Fi naught or gamma I xi into Fi. So if you put gamma I is equal to Fi bar upon xi Fi, and Fi naught by Fi is Ai. So this becomes Ai by xi. Right? ये term है Ai activity. Fugacity of component I in solution upon fugacity of pure component is activity. And so we get activity is nothing but gamma I into xi. So equation 1 is nothing but Lewis fugacity rule modified by gamma I to correct for deviations from ideality. We have seen that before. Gamma I introduced किया हमने. So equation 1 reduces to Raoult's law or Lewis fugacity rule when when xi is tending to 1. Right? That means gamma I is equal to 1 as xi tends to 1. So for pure component, almost pure, जो second component का अगर concentration बहुत ही कम है, right? So it will behave almost like a pure component 1. So in that case, gamma I is equal to 1. That's how we define it. And then in this equation reduces to fi bar is equal to xi fi, because gamma equal to 1 बोला तो it becomes like Raoult's law or Drew's spaghetti rule. So in this case, that is activity coefficient is defined with respect to ideal solution in the sense of Raoult's law. In the sense of Raoult's law means we're talking about almost pure solution, pure solvent, xi tending to 1. That means x1 tending to 1, x2 will be tending to 0. Second component is very, very low concentration. First component is almost 1. ठीक है, समझ में आया? ये आइडियल केस हमने देखा था लास्ट वीक. वी आर जस्ट सेइंग नाउ द एक्टिविटी कोएफिशिएंट क्या होता है उसमें. इन टर्म्स ऑफ पार्शियल प्रेशर हमने डिफाइन किया था लास्ट वीक है पी आई बार इज इक्वल टू गामा एक्स आई पी आई एस एंड दिस विल रिड्यूस टू राउल्ट्स लॉ पी आई बार इक्वल टू एक्स आई पी आई एस. ये हमने डिराइव किया था लास्ट वीक, राइट? एक्स आई पी आई एस. ठीक है, एनी डाउट्स, क्वेश्चंस? So if you have almost pure solvent, if you have two components in the mixed solution, where one component concentration is almost 1 and second component concentration is almost 0 or close to 0, then first component, which is having 0.99 or something concentration, follows Raoult's law, which is nothing but Pi bar is equal to Xi into Pis. That's what this means. Any questions, doubts?
सर वो स्टेटमेंट द प्योर लिक्विड एट द प्रेशर ऑफ द सिस्टम, मतलब यही है ना रेनॉल्ड्स लॉ जो फॉलो करते हैं?
यस, ये हमने स्टैंडर्ड स्टेट में दिखा था ना, Fi by Pi is equal to 1 लिया था, राइट? एंड वी सेड फॉर प्योर कंपोनेंट विस्कोसिटी इज इक्वल टू प्रेशर, राइट? बराबर, वो डेफिनेशन ऐसे लिया था हमने. F by P is equal tends to 1 when P tends to 0, right? So that's what you are saying. When it is almost pure component standard state means they were saying pure liquid or pure gas at the system temperature and pressure. So in this case it becomes yes, equation 4.
सर
Yeah,
सर इक्वेशन 4 में पी आई बार इक्वल टू ए आई इंटू पी आई एस येणार ना, आएगा ना?
ये कहाँ से आ गया? अभी गामा है ना यहाँ पर. तो
सर गामा इंटू एक्स आई इक्वल टू ए आई लेते ना एक्टिविटी.
हम क्या बोल रहे हैं? What are we saying? As concentration of xi tends to 1, gamma I tends to 1. That is the definition of our activity. We are saying that activity follows two, right? We said two ways of defining activity. यही बोला ना हमने. Let's see. Types of ideal behavior. Right? Two types of ideal behavior. One ideal behavior is one, it is pure, almost pure solvent and very little of solute. Second one we'll see later. So let us look at first one. First case is suppose I say 99% water and 1% ethanol. So it's going to behave almost like water because that 1% ethanol is not going to contribute much to non-ideality. Because concentration is very, very low. I'm taking 99, but it can be 99.5. तो जितना कम लेंगे इथेनॉल का उतना contribution going to reduce further. And it's going to behave almost like pure water. Right? So that way, in that case, we are saying that it's almost pure solvent. The solute is very little. It's not going to contribute much to non-ideality. And in that case, gamma is equal to 1. That is the first way of defining ideality. कि almost pure solvent रहेगा, तो gamma is equal to 1. And in that case, one is that Fi bar is equal to Xi Fi. ये वाला कहाँ गया? This will become equal to Xi Fi because gamma equal to 1. And if you write in terms of partial pressure, same thing we had derived last week, that is equal to Pi bar is equal to Xi Pi derive किया था हमने, यहाँ पर इंट्रोड्यूस किया gamma for non-ideal solutions, just like figuratively में इंट्रोड्यूस किया था. And then we say that for ideal solution, This is for non-ideal, right? This term, equation 3 is for non-ideal solutions because the gamma I term is there. But now we say that, okay, what will happen if it is ideal? If it is ideal, that means xi is almost pure component. So gamma I is defined as 1 for xi tending to 1. So in that case, this becomes pi bar is equal to xi into pis. This is Raoult's law. हमने derive किया था last week for ideal solutions. ठीक है? Ritesh, is it okay?
Yes, sir. Yes, sir. Got it, sir.
Okay. So second one is it follows Henry's law. There is another way of defining ideal solution. That means क्या हुई? If we looking at two components, right? Two components लिया हमने. Let's see if I can write something here. Okay, so if we take two components and this, suppose you plot x here on the x-axis and you plot gamma on the y-axis, right? This is 0 and this is 1. So we're defining, first one we defined then when x is equal to 1 in this range, जो भी रहेगा value, whatever it is, doesn't matter. So this is what we are talking about, gamma at x tending to 1. ये हमने बोला gamma equal to 1, right? दूसरा होगा when x tends to 0. If activity coefficient is defined with respect to ideal dilute solution. Dilute solution कब होगा? When concentration is very low, right? So suppose this is x1, right? x1 goes from 0 to 1, तो x2 क्या हो जाएगा? Right? When x1 equal tends to 1, x2 tends to 0. When x1 tends to 0, x2 tends to 1, right? Because total has to be 1. So we defined one for this case and one we are defining for this case. Okay. So if we are defining Henry's law, which follows Henry's law, पहला follows Raoult's law, second one follows Henry's law. If activity coefficient is defined with respect to ideal dilute solution, that is, standard state is defined as hypothetical state where pure component fugacity is equal to Henry's law constant, not equal to pure component fugacity, right? We are saying pure component fugacity is equal to Henry's law constant. So in this case, Fi bar is equal to gamma xi, Fi था, Fi we are saying is equal to Ki. This gamma I prime is called activity coefficient infinite dilution. That means very low concentration of component I. Okay? So in this case, gamma I prime is equal to Fi bar upon xi into Ki. That is how this gamma I prime is defined for infinite dilution. Similar to what that other one, only thing is instead of Fi, we are saying it is Fi is equal to Ki for very low concentration of solute in solution. So fugacity is equal to Henry's law constant. And what we have defined Henry's law is nothing but Fi bar is equal to Xi Ki. So this will be reduced to so if you compare equation 5, this one, and equation 6, if you compare this equation 5 with equation 6, Fi bar same hai. This is the definition of our gamma I prime for infinite dilution, and this is our Henry's law equation, Xi Ki. So in this case, equation 5 reduces to equation 6 when gamma I prime is equal to 1 for dilute solutions, Xi tends to 0. ठीक है, समझा क्या? Ideal state defined for very dilute solutions. Any questions, doubts on this? Just like Raoult's law condition, when we say that one component is maximum, maybe 0.99 or so, we are saying one end is that, the other end is that very low solution solid concentration. When you talk about, say, gas solubility in liquid, that condition may, it follows again Henry's law, and it becomes, activity coefficient becomes 1 when the concentration tends to 0.
सर और जैसे हेनरीज लॉ हमारा गैस और लिक्विड के लिए है, वैसे रेऑल्ट्स लॉ लिक्विड के लिए है ना?
Raoult's law is mostly for liquid, yes. No, liquid में भी ऐसा होगा. Suppose I am talking about, say, oxygen solubility in water, right? So in this case, when I am talking about oxygen solubility in water is very, very low. In this case, what I can say for water, oxygen water system, that is almost 1. Level. And solubility in water is almost in ppm level, and water is going to be almost 1.
सर आवाज ब्रेक हो रही है क्या?
आवाज कम आ रही है आपकी.
ओके, ठीक है. अभी आ रही है आवाज?
कम आ रही है सर.
एक मिनट. ठीक है, so वीडियो बंद किया मैंने. आवाज आ रही है मेरी? Can you hear me now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So
Yes, sir.
I can give you an example. It can be any example. When you look at gas liquid, say oxygen in water or SO2 in water, it can be any gas in water. तो ये क्या हो जाएगा, इसकी कंपोजिशन रहेगी वेरी लो रहेगी, and water is almost pure. So when I talk about water activity, it will follow Raoult's law because it is almost pure water, right? The second component is very low concentration. Okay, the other end of the spectrum is I want to find out activity coefficient of SO2 or oxygen in water. So this concentration is very low. So this is our Henry's law region. समझे ना? So same solution, when I want for one end of the solution, when concentration of water is very high, I can use Raoult's law. When I want activity coefficient for solute, because concentration is very low for a solute, I can use Henry's law. So the same solution, I can use these two laws at the same time. समझा क्या? Example में जो भी हमने SO2 और water के दिया, oxygen water, it can be ethanol water also, doesn't matter. If the ethanol concentration is very low, suppose instead of SO2 it is ethanol, I can use the same thing. So when the concentration is very high, I use Raoult's law. When the concentration is very low, I use Henry's law. Just remember that. That is the way of demarcating when to apply Henry's law, when to apply Raoult's law. Is it clear now?
Yes, sir, clear.
Okay. So let's go to Henry's law now. समझ में आया ना? Otherwise it is very confusing. Just understand कि pure है तो Raoult's law use करने का है, और very dilute है तो Henry's law use करने का. And in that case, when you apply Henry's law, again gamma I is defined as 1 when xi tends to 0. That means for say SO2 in water, for SO2, sorry, SO2 gamma is equal to 1 when the concentration is very low. ठीक है? So to summarize, ये सब भूल जाओ. When it is pure liquid at system pressure and system standard state, gamma I tends to 1 as xi tends to 1. And for ideal dilute solution, Henry's law, gamma I tends to 1 as x1 tends to 1. ये Raoult's law हो गया, right? This is Raoult's law. But this is Henry's law. So gamma 2, suppose it is water and SO2 वैसे लिया हमने, तो water अगर pure है almost, तो gamma is equal to 1 as xi tends to 1 solvent के लिए, और solute के लिए then gamma 2 x2 is tending to 0, gamma 2 is equal to 1. So for the same solution, I can use Raoult's law to calculate activity of solvent and Henry's law to calculate activity of solute. ठीक है?
सर जैसे रेयॉल्ट्स लॉ में क्या रहता है कि हमारा एक कंपोनेंट का ज्यादा रहता है इसलिए ठीक है, लेकिन हेनरीज लॉ में बहुत कम है कंसंट्रेशन, तो फर्क क्या पड़ने वाला है फुगेसिटी को? टेंड्स टू 0 है ना, तो एक्टिविटी तो क्या कैसे मेजर?
बाद में देखेंगे. मेजर करने का, वी आर गोइंग टू सी, वी आर जस्ट डिफाइनिंग नाउ. व्हेन इट इज डाइल्यूट सॉल्यूशन, हाउ इज एक्टिविटी डिफाइंड? व्हेन इट
मींस तब कुछ डिफरेंस रहता है क्या, मतलब इफेक्ट होता है क्या कि टेंड्स टू 0 है तो एक्टिविटी को
होता ही है ना. सी डेफिनेशन इज लाइक दैट ओनली. वी आर व्हेन एज वी स्टार्ट विद आइडियल सॉल्यूशन. आइडियल सॉल्यूशन क्या था? वी सेड, वी आर सेइंग कि almost no volume change on mixing, right? That means one has no effect on the other. They are similar compounds, so then you can say ideal solution. Now we are trying to build in non-ideality by introducing activity or activity coefficient. ठीक है, अगर नॉन आइडियल होगा, आइडियल नहीं बिहेव किया, तो क्या कैसे क्वांटिफाई करेंगे उसको, राइट? हाउ डू यू क्वांटिफाई नॉन आइडियलिटी? सो इंट्रोड्यूस अ कॉन्सेप्ट called gamma I. Now gamma I can be 1 for ideal solution, and when it is ideal, when it is almost pure solvent, or when there is concentration is very low. There are two situations when gamma is equal to 1. That means this will behave as an ideal solution, right? What this means is this will behave like an ideal solution in these conditions. बाद में ये कैलकुलेट करेंगे हम. एक्चुअली gamma is going to be different from 1 in real solutions, and that we'll see how to calculate. But now we are saying, ठीक है, we have defined gamma I for non-ideality, but we are saying in which conditions, under what circumstances it will become ideal. समझ में आया?
Okay. Yes, sir.
Okay. Then we'll calculate gamma. There are many methods of calculating gamma. Just like we had seen many methods of calculating fugacity, right? वैसे we want to see many methods of calculating gamma, and that will tell us, okay, gamma का value क्या है? किसी system में it will be close to 1, किसी system में it will be more than 1, किसी system में it will be less than 1. So there are different situations depending on the systems. But we are saying कि अगर ideal हुआ तो किस condition में ideal हो सकता है? That's what you're saying. There are two extremes only. ठीक है?
हाँ सर.
Okay. So then, let's just like before, we have to see what is the effect of pressure on activity coefficient. जैसे हमने देखा था fugacity पे, we have seen for chemical potentials. Similarly, we have to see for activity coefficient also. Pressure change किया तो क्या होगा? Because our systems, chemical systems are mostly at constant temperature and pressure, but may not be low pressure. अगर high pressure पे operate किया हमने system, तो effect क्या होगा activity coefficient पर? अगर हाई टेम्परेचर पे ऑपरेट किया तो इफेक्ट क्या होगा? सो वी हैव टू सी दैट. ठीक है. वी हैव सीन दिस थिंग, इफेक्ट ऑफ प्रेशर ऑन फ्यूगैसिटी डिराइव किया था हमने. डबा एल एन एफ आई बाय डबा पी एट कांस्टेंट टेम्परेचर वी आई बाय आर टी. एफ आई इज इक्वल टू फ्यूगैसिटी ऑफ प्योर आई एंड वी इज मोलर वॉल्यूम. सिमिलरली फॉर फ्यूगैसिटी ऑफ कंपोनेंट आई इन सॉल्यूशन वी कैन राइट दिस वन इक्वेशन टू double n fi bar bar double p at constant temperature is equal to vi bar by rt, where fi bar is equal to fugacity of I in solution. So if we take 2 minus 1, equation 2 minus equation 1, we'll get this minus this is equal to this minus this. So what we'll get is double n fi bar by double p at constant temperature minus double n fi bar fi upon double p at constant temperature is equal to vi bar minus vi upon rt. So we can write this as double n fi bar upon fi upon double p at constant temperature is equal to vi bar minus vi upon rt. ठीक है. But we know that fi bar is equal to gamma I xi fi. So if we substitute in 3, what we get is fi bar by fi is equal to nothing but gamma I into xi. So we get double n gamma I xi upon double p at constant temperature is equal to vi bar minus vi upon rt. Now we know that composition does not depend on pressure, right? So we can say double n xi by double p at constant temperature equal to 0. इसको ब्रेक किया तो ऐसे हो जाएगा double n gamma I by double p plus double n xi by double t. So second term 0 हो जाएगा, and what we'll get is double n gamma I by double p at constant temperature is equal to vi bar minus vi upon rt. So that is the effect of pressure on activity coefficient. ठीक है. If you really see, ये fi का था vi by rt, right? Activity coefficient is fi by fi bar, right? So it is vi bar minus vi. Intuitively you can write this in by definition of fi bar. ठीक है. Any questions on this? Okay, so let's move on to effect of temperature and activity coefficient. We have seen effect of temperature on fugacity of pure component. Double n fi by double t at constant pressure is equal to hi 0 minus hi upon rt. Similarly for substance in solution, double n fi bar upon double t at constant pressure equal to hi 0 minus hi bar instead of hi become hi bar upon rt square. If we take again 2 minus 1, this minus this is equal to this minus this. What you get is double n fi bar by double t at constant pressure minus double n fi upon double t at constant pressure is equal to hi 0 minus hi bar upon rt square minus hi 0 minus hi upon rt square. Hi 0 cancels out. And what we get is ln Fi bar upon Fi W T at constant pressure is equal to Hi, ये प्लस माइनस एस प्लस हो गया, माइनस HI bar upon RT square. And we can substitute Fi bar by Fi equal to gamma Xi. And again similarly ln Xi by T at constant pressure is equal to 0 because X is independent of temperature. So what we'll get is ln Xi gamma I T at constant pressure equal to Hi minus HI bar upon RT square, which will reduce to the second term will go out just because of this thing. What you get is ln gamma I by T at constant pressure is equal to Hi minus HI bar is equal by RT square. So that is the effect of temperature on activity coefficient. The equations are going to be similar because they are all correlated. They are all related. Fi is related to gamma. Any questions, doubts?
Sir, your voice is not audible.
Voice is not audible. ये इक्वेशन डेरिवेशन देखा? Any doubt on derivation? डेरिवेशन में डाउट है क्या ये? Effect of temperature and pressure.
No, sir.
Not clear.
Sir, it is clear.
It is clear. ऐसा बोलो ना. मेरे को लगा no sir means no, not clear. जब मेरा आवाज नहीं आ रहा तो इमीडिएटली बोलना चाहिए आपने, बिकॉज आई डोंट नो कब प्रॉब्लम आ रहा है इंटरनेट का. आई इट्स वेरी डिफिकल्ट फॉर मी टू नो. सो व्हेन एवर यू आर नॉट एबल टू हियर मी, जस्ट स्टॉप मी, लेट मी नो. ठीक है? अभी आ रहा है क्या आवाज?
हाँ सर, थोड़ा आ रहा है.
थोड़ा ही आ रहा है. सबको प्रॉब्लम आ रहा है क्या? क्या? तो
सर आवाज नहीं आ रहा है आपका.
आवाज नहीं आ रहा है, बिल्कुल नहीं आ रहा है.
अभी आ रहा है.
थोड़ा आ रहा है सर.
आ रहा है. प्रॉब्लम है, नेट का प्रॉब्लम है. इसलिए वीडियो बंद कर दिया मैंने. तो
अब आ रहा है सर, ठीक आ रहा है.
ठीक आ रहा है अभी. ठीक है. किसी को डाउट है जो हमने देखा अभी तक, इफेक्ट ऑफ टेम्परेचर, प्रेशर?
नो सर.
ओके. Okay, so let us see. I check a problem.
हेलो सर.
हाँ बोलो.
हेलो
हाँ बोलो.
सर, अभी हमने फुगासिटी क्यों डिजाइन किया? क्योंकि वो रियल प्रेशर, रियल गैसेस का इफेक्ट बताता है. तो फिर हमें फिर से एक्टिविटी कोएफिशिएंट क्यों डिफाइन करने की जरूरत पड़ा?
Because for solutions, it's very difficult to measure fugacity. So we have to define.
Sir, voice is not clear, sir, at all.
वॉइस क्रैक हो रहा है।
way of introducing.
हेलो,
आवाज आ रहा है मेरा? मेरे आवाज आ रहा है?
No, sir.
हेलो देवेंद्र,
सर नहीं आ रहा है वॉइस। सर इफ पॉसिबल होगा तो हेडफोन्स यूज करके देखो ना। रितेश तुला आवाज येतोय का?
कसलाच आवाज येत नाही
नाही
त्यावेळेस.
आवाज येत नाही. आवाजच येत नाही. सर आहेत का बघ पहिला लेक्चर मध्ये?
सर आहेत ना, स्क्रीन शेअर आहे ना अजून.
हा हा आहेत ते सर. आवाज काय येत नाही सरांचा. हेडफोन मुळे का आवाज येत नाही तुला?
पूर्ण नेटवर्क गेलं पण येत नाही.
अरे कर्सर मूव्ह करायला की सर स्क्रीनवर बघ ना, कर्सर आहे त्यांचं.
सर युअर वॉइस इज नॉट क्लिअर सर.
येतच नाही असं सांग रे. क्लिअर नाही, येतच नाही असं. शिवानीला फोन करा सांगा की. द्या फोनला सरांना.